So far we have learned how to find the center of mass of the system contain point particle. Now, if the system contains point particle like M1, M2, and M3, the location for the center of mass can be calculated using this equation. X bar is the summation of MIXI divided by the total mass Mi. Y bar is equal to the summation of MIYI divided by the summation of Mi. We can combine these two equations and write it in a vector form. So if we write down RCM, the center of mass, equal to X bar and Y bar, and Ri, the position of the ice particle, is Xi and Yi, we can write RCM equals to the summation of MIRI divided by the summation of Mi. Now we want to find the center of mass of a rigid body. So what is rigid body? Rigid body is the object that has a finite shape, and importantly, the shape of this object must not change while it is moving. So consider if I've got this irregular shaped object and I throw it. If its shape does not change, it means that this object is a rigid body. Or I've got a hammer. We know that the shape of the hammer does not change while we throw it in the air. So this hammer is a kind of rigid body. So the key point of the rigid body is it has a finite shape and the shape does not change when it is moving, and that's it. So, how can we actually calculate the center of mass of this irregular shaped object? The answer is easy. We are going to use the idea of point mass. So whenever you've got this rigid body, the first step that we have to do, we have to cut it into small pieces. Like this. And what we do, we are going to consider one piece of mass that we cut. So this piece of mass we are going to call it dm. You must realize that whenever we use this d, it means that this mass is very small mass. And when it is very small, it means that this mass can be regarded as a particle. So basically we divide the whole big object into millions, trillions pieces of particles. And therefore, the equation for x bar, which is the summation of MIXI divided by the summation of Mi, will turns into x bar equals to, so you see that we have to multiply mass and x. So we are going to get this x and dm. This x is the position of this mass, so this point mass here is at the position xy. So we have x times dm, and then at the bottom we have this mass dm here. And in the integration, and in calculus, the summation means integration. So we are going to turn the summation signs into the integration like this. So this is the equation for the center of mass of the rigid body. So let's have a look at this example. How can we use integration to find the center of mass of a rigid body? So the first example, we would like to find the center of mass of a rigid cone, solid cone. So we've got a cone like this. And what happened is we are going to look at this cone from the side. So this is the side view of the cone. This is the side view of the cone. So we have this, this, and this. This cone has the radius r and the height h. So we have here r and h. So the coordinate of this endpoint here is r is h. R is hr. This h actually should be here along the x-axis. So this is h and r, and the coordinate at the apex of the cone is 0, 0. So how can we calculate the center of mass of this cone? Of course, we have to cut this cone into small pieces, and we are going to cut it into discs like this. So we've got this disc here, and you see that to build up the cone, we can stack the disc of different radius, starting from the bottom like this, and we stack the disc up to the end to build up the cone. So we are going to stack up the discs with different radius to build up the cone. So this is the idea of calculus. We build the big thing from a very, very small object. And in this case, we are going to cut it into small disk, and we are going to say that this disk has the thickness, very small thickness dx, because you see that the thickness is along the x-axis. The thickness of the disk is along the x-axis, and the center of mass of this disk is at this position here on the x-axis. So the center of mass of the disk is at x0. So we say that the center of mass of the disk is at the distance x away from the origin, and the radius of this disk is given by this distance y, because it's along the y-axis. Now we are going to find dm. The small mass of this disk is equal to rho times dv. So this is the density times volume. This is the density times volume. So density is given by rho, and the small volume is dv. And the volume of this disk is the base, which is pi r squared. The radius is y, so we have pi y squared times the thickness, which is dx. So now we have dm. The mass of the small disk or thin disk is rho pi y squared dx. So we have rho pi y squared dx. And the center of mass of the disk is x, and therefore x times dm is given by rho pi y squared times x dx. And then we are going to integrate this. We are going to sum this. So we are going to start our stacking process from the bottom to the end here, or you can see from this diagram, we are going to start stacking like this, from x equal to 0 to x equal to h. So we are going to integrate this from 0 to h, from 0 to h. And then we can bring out the constant of integration, which is rho pi. No, not constant of integration. We can bring out the constant from the integral. So we have rho pi outside the integral, and we have y squared x dx. Now, what is y squared? Y is the radius, and you see that the radius changes as we move along, or as we stacking up the disk, the radius changes. So we have to find these relationships, and the relationship can be found using the similar triangle. So we have this big triangle here. So this big triangle This side is r and this side is h. Now we are going to consider this small triangle. So we have this small triangle inside the big triangle. This side is x and this side is y, and therefore we have y over x equal to r over h, and so we have y equal to r over h times x. We are going to plug this into this integral, so we have rho pi integration from 0 to h, and we have r over h times x squared times x dx. So we have rho pi r squared over h squared, the integration of x cubed dx from 0 to h, and this is rho pi r squared over h squared, x to the power of 4 divided by 4 from 0 to h. So we've got rho pi r squared over h squared times h to the power of 4 divided by 4, and you see that h squared cancel with h to the power of 4, so we've got h squared. So in this case we have the integration of x dm from 0 to h equals to rho pi r squared h to the power of 2 divided by 4. And the integration of dm from 0 to h, this is the total mass. We are going to get 0 to h, and dm is this terms here, rho pi y squared dx. So we get rho pi, the integration from 0 to h, y squared, which is r squared over h squared x squared dx. So we've got rho pi r squared over h squared x cubed divided by 3, and we plug in the limits. So we've got rho pi r squared over h squared h cubed over 3. So the mass is 1/3 pi r square, and you see that h square cancel with h cubed, so we've got h here times rho, and there is no surprise because this term here is the volume of the cone and this rho here is the density. So we now get back to this relationship, volume times density, so we get the total mass. And now the center of mass xcm is given by rho pi r squared h squared over 4 divided by the total mass rho pi r squared h over 3. You see rho pi cancel, r squared cancel, so I've got 3h over 4. 3h over 4. So it means that if I've got a cone like this, the center of mass must be below the apex by the distance of 3h over 4, or it is above the base by the distance of h over 4. So this is the center of mass of the cone. This is how we use the integration to find the center of mass of the rigid body.